Okay, year 11, we are gonna go on to speed time graphs and velocity time graphs today. But before we do, I just want to recap what we looked at last day with distance time graphs and displacement time graphs. So I'm just looking at this one on page 165 because that allows me to summarize everything. Okay, so if we have a displacement time graph, then if it's a straight line like this, it means something's traveling at a constant velocity. Okay, and we know that because the gradient is staying consistent. So for every second that passes, the change in the displacement is the same amount. It's going up by the same amount every second. So that's the first thing I suppose you need to know. If it's a curve like this, then that means it is changing speed, and you can tell whether it's speeding up or slowing down by what is happening to the steepness of the graph or what is happening to the gradient of the graph, because remember the gradient is just a measure of the steepness. Okay, so seeing this one here, it's getting steeper. So this one here would be showing an object that is speeding up, because at the start here it was going quite slow, the gradient's shallow, and then at the end it's going quite fast because it's a really steep gradient. So in the same amount of time here, the change in displacement is only slight, whereas over here, the same change of time, the change in displacement is a lot more, so it must be going way faster there. Now, I did mention very briefly last day, if you had a curve like this, the way you would find the velocity, at a point on this, you would have to draw a tangent to the curve. I did say in that lesson that you're not going to get asked to do that, but just in case you're interested in what that is, a tangent is just a line drawn at any particular point on the graph, a straight line that shows like how steep the graph is at that particular point. So at this point here, I've done an estimate, and it is always just an estimate, that the graph is this steep, and then I would find the gradient of this wee straight line here. Okay, so the important things that you need to be able to do, you need to be able to recognize and remember that the gradient of a distance time graph tells you the speed, and the gradient of a displacement time graph tells you the velocity. And then there is just a wee reminder down at the bottom of how you calculate the gradient. I'm going to add in a little extra example here, so get a pen out so that you can add it in as well. Right, I'm going to talk you through this, and then once I'm done, pause the video and get it copied down. Don't try and write it down as I'm going over it, I'd rather you listen to me. Okay, so I've got a displacement time graph here, and to find the gradient, I've just picked 2 points on the graph, and I'm going to be applying this. So the gradient is the change in the y divided by the change in the x. Other ways that could be worded would be rise over run. So I have picked these 2 points. Okay, so the coordinates of this point is 5, 8, right? And the coordinates of this point is 2, 3. Okay, so whenever I'm always talking about calculating gradients, I would talk about using a big triangle. So you're always trying to pick 2 points which are really far apart on your graph. You wouldn't pick like 2 points right beside each other. Okay, so if I'm doing this, I'm going to call it rise over run. It's just my preference. So gradient is rise over run. Okay, so the rise is how much, going from one point to the next point, how much your graph has gone up by. So this has gone up from 3 to 8, so that means my rise is 5, and the run is how far it's gone across by. So this has gone from 2 to 5, so that's 3. So it's 5 over 3, which gets me 1.67 if I just go to 3 significant figures. And that's going to be meters per second, because we know the gradient of a displacement time graph gives us, oh, I've written that like A level, fixed meters per second, sorry. We know the gradient of displacement time gives us velocity. The other way that you could figure that out, displacement is in meters and time is in seconds, so you're dividing meters by seconds, gives you meters per second. Okay, pause, copy that in as a wee example of finding the gradient. Okay, so on to page 166 and speed time graphs. This is our main focus for today, and there's some basic ones that we need to know. So if you have a graph like this, and you should be filling yours out with me. So speed against time. If we have speed time graph and it is like this, one of the most common mistakes that people make is they apply the rule from distance time graphs here and they think, oh, that must mean it's stopped. It's not. As time is continuing on here, the speed is just staying constant. So a graph like this shows you something that's traveling at a constant speed. Okay. Okay, next one. If we have a graph like this, so again, speed time, like something like that, then obviously the speed is increasing as time's going on, and because it's a straight line, it's increasing regularly, so it's accelerating at a constant rate. So write that in for me. Speed is increasing, so object must be accelerating. Okay, get that in. Next one, I'll fill in now. Okay, so here's our next one with a constant downwards gradient. As time is increasing, the speed is decreasing, so this one must be decelerating. Okay, make sure you get that written in. Right, over on to 167 then. If you have two constant gradients here like this, we need to be able to compare the two of them. So it's very the same technique that you would use with the distance time graph and the displacement time graphs. Look and see how much each is changing by in like regular intervals. So do you see how in this first little bit, this one, the speed has only increased a bit, whereas this one, the speed has increased a lot. So this one is like has a much higher acceleration. Okay, so that's just summarized here. Both the lines show increasing speed. They both reach the same top speed, but the bottom one, this one, takes longer. What's the difference? The top one has a greater acceleration. So here's what we need to be able to do with speed time graphs. I haven't talked about this yet, give me a wee second and I will, but the gradient of the line, so that same process we used with the displacement time graphs there, if you calculate the gradient of the line, it'll give you the rate of change of speed. And another little trick here is that the area underneath a graph is equal to the distance travelled. So I think this kind of makes sense with this. If we look here, if we calculate the area underneath this, remember distance equals speed times time, and that can only be applied if something's travelling at a constant speed, but this isn't travelling at a constant speed, it's constantly changing. So by calculating the area underneath this here, we're really just calculating the average speed multiplied by the time. The average speed is going to be half of the final speed, and then you're going to multiply that by the time, and that is exactly the same as calculating the area of a triangle, half times base times height. Okay, so we'll see this come up in questions, and it tends to come up in questions like where it's, you know, like when something goes here and then goes here and then does all that. So it tends to come up like that. It will come up in some of these questions that we're going to be doing. But these are our rules that we need to know. Okay, now same way as with displacement time graphs, these same rules can also be applied to velocity time graphs. And again, I've summarized this all here for you on page 168. So something like this shows a constant acceleration. Because acceleration is the rate of change of velocity, then the gradient of a velocity time graph is acceleration. Make sure we know this. And the area under a velocity time graph is displacement. So that's the exact same as with the speed time graphs, but because velocity is a vector and direction matters, then there's a wee sneaky thing that can happen here. So if you look at this one down at the bottom of the page, okay, so let's think about what's actually happening with this object. So it's accelerating, then it's traveling at a constant velocity. and then it's decelerating, so it's slowing down. Here it's stopped for a wee while because the velocity is 0. Here it's accelerating, but it's in the opposite direction, and that's why it's down underneath. Then it's traveling at a constant velocity, and then it's decelerating. So that can be a little bit hard to get your head around, with like the fact that an upwards gradient here is accelerating and technically an upwards gradient here is decelerating. But if you think about the magnitude of the numbers we're talking about here, and by that I just mean the numbers involved, the size of them. Here, whenever you move away from your x-axis, your numbers are getting bigger. Whenever you move away from your x-axis here, your numbers are getting bigger. So if our velocity was -1, -2, -3, well, -3 meters per second is obviously faster than -1 meters per second. So here it's decelerating, it's getting slower, but the negative is just all about the direction. So the one thing we need to be careful of here, if you got a graph like this and you were asked to calculate the total distance that the object had travelled, well, you would calculate this area here, and then you would add this area here. However, if you were asked for the displacement, then you calculate this area, but you would take away this area, because remember it's had that change in direction. It's going the opposite direction. So it's like it's gone over here, it stopped for a while, and then it started to come back again. So its displacement is going to be much less than the total distance that it travelled. Okay, so displacement and then distance travelled is that. Okay, now last day we did, well, most of us did this question here. What I want you to do today then for the rest of the lesson is question 2 and question 3 on page 170. But don't go yet, because we need to do a retrieval roulette. I'm going to go over all of these questions next day for you, okay? But let's do our retrieval roulette now, because I forgot to do it at the start. Okay, so first thing you need to do is to pause the video and then answer all these questions. So pause the video now. Do you have them answered? Okay, now use these answers to mark your work. The only one that isn't there is question 2, and I think it was to sketch the plum pudding model. So on that you should have your positive blob of matter, and then dotted in around that your negative electrons. Okay, but the rest of them you just mark there. So I'm going to be asking to see this, your marked retrieval roulette, and I'm also going to be asking to see, get those marked and paused if you haven't done that already. I'm also going to be asking to see your answers to the questions on page 170. Okay, so I'll be on Google Meet for the last 15 minutes of the lesson there to answer any questions if anyone is stuck. Bye.